Hey everybody. Let's see. So this is going to be a video on the inverse trig functions. Kind of what I'd like to do in this video is obviously I want to look at all six of the inverse trig functions, look at those graphs. But the really important parts are going to end up being sort of the domain and the range. We'll talk a little bit about how to use inverse trig functions when we're solving problems. And I also just kind of along the way, I want to give some kind of motivation for how these inverse trig functions are kind of derived. So what I have here right now is the graph of the inverse sine function. So this is what it looks like. And this is it. It has a definitive sort of, you can think of it as like a starting point and a definitive ending point. It doesn't go on forever like how all of these other functions, the functions themselves do. So some key points. The domain of sine inverse is -1 to 1. The range of sine inverse is -pi/2 to pi/2. So I want to spend a few minutes kind of deriving all of this so that it doesn't seem like it's just coming out of nowhere. There is some, of course, like everything with math, there is a lot of rhyme and reason to why all of this is the way that it is. So to begin, let's talk about, here's kind of the motivation for even wanting to develop these inverse functions. Suppose that we want to solve a problem sort of like this. Sine of theta equals 1/2. And then we're asked, like, what is theta? Well, where does sine of theta equal 1/2? At least if we're going around the unit circle just one time, it's at theta equals pi/6, and at theta equals 5 pi/6. So that's just one time around, but there are infinite places where sine theta equals 1/2. If we add integer multiples of 2 pi to each of these, because the period of sine is 2 pi, then we end up with this is all of the solutions, well, half of all of the solutions where sine of theta equals 1/2. K is an integer there. Same thing with 5 pi/6. If we just repeatedly add 2 pi, then we end up with these are all of the solutions for where sine theta equals 1/2. Now, we want to get to a place where we can take something like sine theta equals 1/2 and write it as a function and say, okay, well, then that means that theta equals the sine inverse of 1/2. And we want this sine inverse to be a function. What makes something a function? It means that every input receives exactly one output. So any input that you provide to a function, it gives some output, and it gives only one output. But right now, without having like restricted anything at all, the solutions to theta equals sine inverse of 1/2 are the same as the solutions to sine theta equals 1/2. And there are infinite solutions, meaning without having any restrictions at all, just what I've done right here, theta equals sine inverse of 1/2 has infinite outputs, meaning without restricting things, sine inverse right now is not a function. We want it to be a function though, so how do we do that? So to make this a function, what we do is we restrict. And technically we restrict the range of this, but really what that means is we restrict the domain of sine so that it's 1-to-1. Because kind of the criteria for if you have a function and you want the inverse of that function to also be a function, then the original function has to be 1-to-1. So we need to restrict the domain of sine so that it is a one-to-one function. In particular, we want to restrict it in such a way that it grabs every possible output value of sine. So here's kind of what I mean. Here's the regular sine function. It goes like this, just forever and always. Oops. So this is sine of x. And this is not one-to-one. How do you know? Well, if a function is one-to-one, then it'll pass the horizontal line test. And if you put a horizontal line through here, that's where you can see there are sort of infinite solutions to certain equations. All right, so we want to restrict the domain of this sine function so that it's one-to-one, and then that way we can just invert it to get the inverse sine function. Well, we have infinite choices of doing that. Again, we want to choose some interval of the domain where the output of sine on that domain captures every possible output. And here's one place of doing it, and this will be the place that we restrict it so that we can create the inverse function. It's between these two values. So take half of a second. What are these values? I know that I kind of made this graph funky, but we can talk about what these two values are. What is the closest place nearest place to the origin where sine of x equals -1? That's at negative pi over 2. And the nearest place to the origin where sine equals +1, positive pi over 2. Oops. And this interval right here from negative pi over 2 to positive pi over 2 grabs every possible output in the range of sine. The range of sine, remember, is -1 to +1. So every value in the interval from -1 to +1 is being touched by this graph. So here's our restricted sine function. Restricted from negative pi over 2 to positive pi over 2. Let's see here. There it is. Right? That's just taking that same thing. So this is sine of x on negative pi over 2 to positive pi over 2. Right? Okay, so how do we derive the inverse sine function from this restricted sine function? Well, when we have a one-to-one function, kind of two things. On the one hand, like if you want to find the inverse of a function, you can swap x and y and solve for y. So remember our old friend y equals mx plus b back from college algebra. If we wanted the inverse of this, swap x and y, so write this as x equals my plus b, and then solve for y. So what would it be? Y equals x minus b over m. This is the inverse of the given linear function, right? So it's the same thing with sine, that we could do that, although it's not all that helpful because all that you end up with is exactly this sort of thing, that the inverse is just equal to the sine inverse. An easier way of doing this, especially so that we can kind of plot all of this onto a graph, is that any point xy that is touched by the original function corresponds to the point y comma x on the inverse function. So taking coordinate pairs and just flipping them tells you coordinate pairs of the inverse function. So that's what we'll do with our new restricted domain function, is we're just going to grab some points and then we're going write out the coordinate pairs, and then we're going to flip the coordinate pairs to derive some of the points. All right, well, what are some of the coordinate pairs that are touched on this restricted domain sine function? Well, moving left to right, there's negative pi over 2, comma -1. It's not really listed on here, but it's a nice convenient number to work with, is that at negative pi over 6, what is the sign of negative pi over 6? Take a second, maybe pause the video and think about it. The sign of negative pi over 6 is -1/2. Right, so it goes through right there. It goes through the origin. And these are all from regular sine, right? So it also goes through pi over 6, comma 1/2, and through pi over 2, comma 1. These are all from the sine. Those are all values that are touched by sine of x. And in particular, again, we're just restricting the domain. So what are the values that are hit by sine inverse of x? Well, just flip the x and y coordinates of these. So negative 1 comma negative pi over 2, that's one value. Negative 1/2 comma negative pi over 6. The origin, still. 1/2 comma pi over 6. 1 comma pi over 2. So these are all points that are being captured or touched by the inverse sine function. So we can just now go ahead and graph these points. And we're going to get the graph that we already saw, so I'm not going to put too much precision into it. But the main thing is sort of notice the domain of these points that we just graphed. The domain goes from -1 to +1. What is the range? The range goes from negative pi over 2 to positive pi over 2. All right, so the domain right here, -1 to +1. The range, negative pi over 2 to positive pi over 2. And then we can just plot a couple of these points. So the nice easy one is the origin. We have the point -1 comma negative pi over 2. We have negative 1/2 comma negative pi over 6. So that's like splitting this into thirds. What, about right there or so? 0, 0, 1/2 comma positive pi over 6, and then 1 comma pi over 2. And when we kind of connect these dots, we get the sine inverse function that we were just looking at. Okay, so that's what sine inverse looks like. Follow along with my notes so I don't say anything too stupid. Right, so and notice like that, so with our restricted sine function right here, this is the domain, this is what we restricted the domain to, and the range doesn't get restricted. The range, we intentionally chose this domain so that it still captures the full range of sine is -1 to 1. But notice that with inverse functions, the domain and the range flip. So the domain of the original function becomes the range of the inverse function. And really importantly, the range of the original function becomes the domain of the inverse function. Another way to kind of think about this, like thinking about why we choose this particular domain, or why this ends up being the range. How should I say? Why we in particular, sorry, I'm like stumbling over my words here. Why we chose to restrict the domain to negative pi over 2 to positive pi over 2. Another way to think about that comes from the unit circle. So think about the unit circle. And think about, like, if we wanted to just kind of draw an arc along this circumference that would capture every output of the sine function, right? So kind of think about what happens. Like if we start right here, then as a point moves counterclockwise, then we hit, all right, well, right here is like pi over 6, so sine of pi over 6 is 1/2, and then up here, sine of this is √2 over 2, and then sine of pi over 3 is √3 over 2, and sine of pi over 2 is 1. But then what happens when we keep moving forward is we just double up on these points that we just hit. Right, here's where sine is once again √3 over 2, and now sine is √2 over 2, and then here sine is 1/2, and here sine is negative, sorry, not negative, it's 0. Sine over here is 0. So like this top arc, the outputs of sine, they repeat each other. Same thing on the bottom arc. So if you think about taking like this arc from the bottom of the circle all the way up to the top, all of the possible outputs of sine are being captured by this arc right here. Down here is where sine is -1, negative √3 over 2, negative √2 over 2, negative 1/2, 0, positive 1/2, positive √2 over 2, positive √3 over 2, and 1. So this sort of arc covers all of the outputs of sine. And what is this arc? Well, thinking about it as like a continuous interval, normally we would talk about down here as being 3 pi over 2, but that's the same. 3 pi over 2 is coterminal to negative pi over 2. And then up here is positive pi over 2. So that's kind of one way of thinking about how we restrict the sign, the domain of sine, so that we can get every possible output of the sign. So in any case, this is what the graph looks like. The really important pieces are, again, the domain and the range. Usually the graph is not quite so important. I can see a world where, I don't really ask this in my classes, but I can see a world where a teacher might give you graphs of inverse sine functions and say, which one is this? And you have to answer that. But in general, the domain and the range are the really important parts, and we'll get there in a little bit. First, I want to go through the rest of the sine functions, the rest of the trig functions, and then I'll talk about why the domain and the range are really important. Really quickly before I move on, just so you know, naming conventions, we sometimes say, we might say something like theta is equal to the sine inverse of x. Actually, I have two kind of quick notes that I'm going to make. The first one is that sine inverse goes by two names. We call it sine inverse. We also call it the arc sine of x. So sine inverse, arc sine, the exact same thing. If I say, what's the sine inverse of 1/2? And then I ask you, what's the arc sine of 1/2? Those are the exact same questions. Interchangeable, sine inverse and arc sine. That's the first thing. The second thing that I'll notice, or that I'll note, is that sine inverse of x is not 1 over sine of x. So this -1 notation, it gets a little bit overloaded in math, because if that -1 exponent, if it's attached to a number, then it means reciprocal, right? Something like this. 1/2 to the -1st power is 2. So when that -1 exponent is attached to an actual number, it does mean reciprocal. When the -1 is attached to a function, it does not mean reciprocal. It means inverse, right? And we already have, we don't need to use the sine inverse. We wouldn't need to use this for the reciprocal anyways, because we have a name for the reciprocal of sine. Do you remember what it is? It's cosecant. So just be kind of careful about that. Sine to the -1 power, sine inverse, is not the reciprocal. Okay? It's not cosecant. Sine inverse is a function itself. So those are the two notes that I'll make. And then I'll also say this big sort of note too about sine functions or trig functions, inverse trig functions. Inverse trig functions, they take real numbers as inputs and they output angle measures. That shouldn't be too much of a surprise, because the normal trig functions, they accept as inputs angle measures and they output number values. So that's being flipped now. Just something to kind of remember. Inverse trig functions output angles. They give you angles. All right, so now let's look at the other the other trig functions. So we'll start with cosine, and kind of what I would like to do now is, at least with cosine, I'm going to do a little bit of justification, kind of like we did with sine. After that, though, I'm just going to show you the graphs and the domain and the range and everything like that. So cosine of x. First, we want to kind of think about, how do we want to restrict this domain? So again, think back to the unit circle. How do we want to restrict the domain? Because we can't just, cosine is not 1-to-1. So we have to restrict the domain before we can define the inverse of it. So how do we restrict the domain of cosine? Well, again, we want to capture, like, if you think about it in terms of the unit circle, we want to capture an arc of the unit circle that outputs every single possible output. So the range of cosine is -1 to +1. We want to find an arc of the unit circle that grabs every output for cosine from -1 to +1. And that arc is this top piece, right? So right here, if we, again, think about a point starting right here on the x-axis and moving counterclockwise around the circle, and think about cosine at each of these points. Cosine of pi over 6 is √3/2, √2/2, 1/2, 0, -1/2, -√2/2, -√3/2, -1. So this top arc grabs every output, every possible output of cosine. What are the angle measures of that top arc? It's from 0 to pi. So we restrict the domain of cosine to 0 to pi, and that's how we grab the inverse. So cosine inverse, it's going to have, again, its domain. The domain of an inverse function is the range of the function itself. What's the range of cosine? It's -1 to 1. So the domain of the inverse function is -1 to 1. And the range is exactly the restricted domain that we just talked about, 0 to pi. So what does this graph look like? Well, again, we could do the same thing as what we did last time, and we can think about just like some of the coordinate pairs that occur over here and kind of flip them. So let's do that. A couple of coordinate pairs for cosine are, right here is 1, 0, and we'll just sort of pick like the convenient ones. Like right here is pi over 3, 1/2. Then there is pi over 2, 0. Let's see, what are some other convenient ones? There would be 2 pi over 3, -1/2. And there would be over here pi, -1. Okay, so what does that mean? It means that the cosine inverse then is going to go through the points. Just flip all of these. It's going to go through 0, 1. It's going to go through 1/2, pi over 3, through 0, pi over 2. Wait a second. Sorry, I'm silly. You probably saw this and you're like, wait a second, that's not right. This is 0, 1. So this should be 1, 0. Sorry about that. This part is not too important anyways. Again, the graphs, sort of important. Domain and range, mostly important. Because that's when we're going to use these things, is just kind of calculating some inverses. All right, so what does this graph end up looking like? Well, the domain -1 to +1, range is 0 to pi. So here's 0, we'll say up here is pi. All right, let's plot some of these. Well, we go through the point -1, pi, so that's up here. We go through the point 1, 0, which is down here. We go through the point 0, pi over 2, which is right here. Let's see, and just to get the curve that this thing looks like, we'll go through the point 1/2, pi over 3. So here's 1/2, splitting this thing into thirds. It's, I don't know, about right there. So it's starting, the way that I have these, it's looking like it's going to be a straight line. It's not. So it actually should, my graph sucks. I'll give you the form of how this thing looks though, because it still has some curve in there. It's kind of like this. Okay, here's the cosine inverse. This is the graph. So domain is -1 to +1, range is 0 to pi. All right, so now what I want to do is just kind of like speed run these other graphs. I'm just going to show you what the graph looks like, write out the domain and range, and then we'll look at, maybe I'll actually make a separate video looking at how to use these in practice, since this is already getting kind of long, turning into kind of a long video. So here's the tangent inverse of x. So tangent inverse, remember, it's got asymptotes and it's got like little strands between each of the asymptotes. We're just going to choose one nice asymptote, one pair of asymptotes that are sort of right around the origin. Where does that pair of asymptotes occur at? Negative pi over 2 and positive pi over 2. And those are, in tangent, those are vertical asymptotes. So in tangent inverse, they become horizontal asymptotes. And then tangent goes through 0. It's going to do something like this. Tangent inverse. About cotangent inverse. Let's see. Oh, right. So the domain of this thing is all real numbers. Why? Because the range of tangent is all real numbers. The domain or the range of tangent inverse is negative pi over 2 to positive pi over 2. So again, you have to restrict the domain of tangent in order to get the inverse. Cotangent, really similar graph, just slightly different orientation, different asymptotes. So the asymptotes of cotangent inverse are going to be through x equals 0 and x equals pi. It goes through pi over 2, and the orientation flips. So it's like this, and then they approach the asymptotes. So there's tangent and cotangent. And lastly, let's look at secant inverse and cosecant inverse. Whoops, very last thing that I'll note here. What's the domain on this? All real numbers. What's the range? Which hopefully you can just read these off of the graph. 0 to pi. Right, next is the secant inverse of x. And these ones end up looking a little bit funny. They're kind of fun. Remember, secant and cosecant, they're sort of like the repeating u's. They also have asymptotes, but they're like these upward facing and downward facing u's. What does the inverse of these things look like? Well, secant inverse, let's see here, its domain is everything outside of the interval from -1 to +1. So negative infinity to -1, and then 1 to infinity. And the range, let's see, there's an asymptote at pi over 2. There's also, let's see, I guess it's not an asymptote, but I'll just sort of list this point, pi. So it starts over here. Make my asymptote first. It starts here at 1, 0, and then it shoots off to the right towards the asymptote. And then it also, on the left, I guess it technically ends here at -1, pi. It moves off towards negative infinity, like that. So there's secant inverse. The domain is negative infinity to -1 union 1 to infinity. The range is, it must be 0 to pi over 2. It doesn't ever touch pi over 2. It skips right over it and then goes from pi over 2 to 1. Yeah. Sorry, not 1. Pi. Hopefully I can read the range off of my graphs. It's questionable now. All right, and then cosecant inverse of x. It's the very last one. And yeah, you probably see me like looking at my notes here. No, I don't memorize what these things look like. And these ones also, like, me personally, I really try to avoid actually using the reciprocal inverses. If I have an equation that I'm working with, or a problem that I'm working with that involves a cosecant inverse, I'll try to remanipulate it into like a sine or cosine or whatever. So this one's kind of cool. It sort of does the opposite. So it hits 1, pi over 2, and then it comes down towards the x-axis. That's where the asymptote is. And then similar idea over here, negative 1 comma negative pi over 2 moves upwards towards the x-axis. There they are. So what's the domain of this? Well, it must be negative infinity to negative 1, bracket, union, 1 to infinity. And then the range must be negative pi over 2 to 0. It jumps over that, and then 0 to pi over 2. Okay? So there are the inverse functions and kind of the motivation behind how they are derived. I'll make another video in a minute here about how to kind of use these things for solving some problems. If you have any questions at all, let me know.